and 10.4. We're what? What'd you say?
Okay, nothing.
Yeah, I'm just gonna do them both at once. It's not terribly difficult. 10.4 is just a special case of 10.2. I'm going to just talk about them right away. So we are going to be talking about Fourier series. That's 10.2, and Fourier series odd and even functions, which is what 10.4 is about. Pronounced for being it's French, obviously I have to write phonetic. Fourier series. Okay, alright.
Fourier.
Fourier. How do you even write that? Yeah, you say four with a French accent. French accent four. Okay, so basically what these are, sort of what Taylor series does do for analytic functions, right? You just take a random function, you want to write it as like an infinite polynomial. Fourier series will do for periodic functions, right? So you're going to take a random periodic function and you're going to write it as a series. And so the idea behind Taylor series was you wanted to write your function in terms that were really easy to deal with, right? So polynomials were really nice. They're easy to integrate, easy to differentiate, etc. So now you're thinking, okay, what are some nice periodic functions that we know about? The nicest ones we know about, the periodic functions. Sine and cosine. Right, so basically a Fourier series is just taking a periodic function and writing it as a series of sines and cosines. Right, that's sort of the backdrop of this. So I'm just going to remind you what a periodic function is. Periodic function with period t greater than 0 is a function f of x which has x plus t in its domain whenever x is in its domain. And f of x plus t is just equal to the original value of f of x. Right? So for sine and cosine, of course, big T, well, there are several t's that will do this for any periodic function. The smallest t for which this is true is called the fundamental period or principal. Example. Principal period for sine x and cosine x is t equals 2 pi. These guys are periodic with period 2 pi. That's the smallest positive number for which they actually start to repeat their values. For tangent, it's pi, etc. So you get the idea. Okay, so that's what a periodic function is. It's just a function that does the same thing over and over, and it does it within some on the basis of some interval, which we call t here, because they usually think of it as time. We take a convenient series form. periodic functions. Okay, so I wrote here about Taylor series, but I already just said that. I don't think I need to write that down. One thing we shall ignore issues of convergence. And just assume our Fourier series Right, so convergence is dealt with in section 10.3. It's not really in our syllabus. There's this whole theorem that you have to go through. And, we don't really need it. I'm not going to talk about it because we're short on time. So we're just going to assume that these guys converge to the function. And so now let's get to the point. Suppose f of x is a 2L periodic function. That is, its principal period occurs with length 2L, i.e. it is principally periodic on, let's say, some interval between minus L and L, which means the length of this will be 2L. So you can sort of center this periodic function around the y-axis, going a distance L in one direction and L in the other direction, so the whole length is 2L, and that period is repeated. Right? So it's a 2L periodic function. We use 2L because in the formulas there would be halves everywhere, and we don't really like halves, and we just multiply by 2 to have it in a nice form. There's no real reason for the 2. There are formulations that just use, the period is L, right? But we do it with 2L. Okay, so suppose this is a periodic function that has a Fourier series. Then this series has the following form. I can write f of x as a0 over 2 plus the series from 1 to infinity of an cosine n pi x over L plus bn sine n pi x over L. So you want to write it as a linear combination of sines and cosines. The coefficients we're going to have to figure out. And these are functions whose period would be 2L. Right? Back in pre-calc, you learned how to find the period of a random cosine or sine function. Right? And I'm just going to tell you the formula for the coefficients. The coefficients, so this is the first thing you need to know.
This is like the wave function in physics, right?
Yes, it's used to model waves all the time, because waves are periodic. I'm going to talk about some of the useful, I'm going to mention some of them soon. But coefficients are given by the coefficients I mean these A's and B's. The so-called, of course Euler has to be involved. Euler Fourier formulas. And these are the following. A(n) is equal to 1 over L times the integral from minus L to L of f of x cosine n pi x over L dx. All right, so our coefficients are given by integrals. Remember, with Taylor series, our coefficients were given by derivatives. In this case, if you can derive the fact that they're given by integrals, your Bn would be 1 over L, integral from minus L up to L of f of x sine n pi x over L dx. These are also very important formulas for you to know. So you need to know what the general form of a Fourier series looks like, and you need to know how to find the coefficients. That is very important. They don't give you this information. You're going to need to memorize this. Right? So they tell you what some Laplace transforms are, but they don't tell you give you formulas for Fourier series. You just have to remember that. Note the A0 is just given by 1 over L from minus L to L of just f of x dx, right? Since when your n is 0, right, because it's A0, you plug in n into the cosine of 0 is 1, so you just get f of x, right? So to find the A0 term, you just integrate the given function from minus L to L, multiply by 1 over L, and then for the rest of the a's, you can use that formula with the cosine. All right, what else do I want to tell you? Okay, now I'm going to talk about 10.4. Now, suppose f is an odd function. I believe I spoke about odd functions earlier this semester. You guys remember what those are, right? Of course, it's in Calc 2. 2 semesters ago.
Cosines?
Meaning f of minus x equals minus f of x. Any function that does that is symmetric about the origin. Sine x cubed x to the fifth, any odd degree polynomial of single term has this property. And more importantly for us is that if you integrate an odd function on a balanced interval, what is the result?
0.
It will be 0. Right? This is when f is odd.
What function is if we rotate it 180 degrees, it would be the same function?
Yeah, so it's like sine is an example, right? So if you just rotate it about the origin, right? If you take the side, flip it, and then flip it again, you get the other side, right? Functions that do that are called odd functions. If you integrate them over a balanced interval, you get 0, and notice that our integrals are on a balanced interval. So knowing that a function is odd can actually cut down some of the work we have to do. Essentially what's going to happen is the following. So, since f is odd, then f of x times cosine of n pi x over L will be odd. Right? Because an odd function times an even function is odd, right? So if you replace x with minus x, this gives you a negative sign. If you replace x with minus x, this makes no difference. So overall, the function changes by a negative sign, right? So it means that this is actually an odd function, which means the integral from minus L to L of f of x cosine n pi x over L dx will be equal to 0, which means all your an's will be equal to 0. So, if f of x is odd, we can write f of x equals just the series from n goes from 1 to infinity of bn sine n pi x over L, where all your an's will be 0, and your bn's are given by 2 over L from 0 to L of f of x sine n pi x over L. Right? This is because if f is odd, then f times sine is even, and then if you integrate an even function over a balanced interval, you can just double the integral over the half interval. An odd function times an odd function is even. So that's why we can do that. So notice here, if your function is odd, its Fourier series will only have the sine terms, right? For this reason, the Fourier series of odd functions are called sine series. So if you're on a final and they say, find the sine series, it means they want you to think of the function as odd, ignore all the a's, only find the b's, and write that as your answer. Similarly, if your f of x is even means f of minus x is equal to the original f of x. Functions like cosine have this property. Right? Notice here, if you put an x value, it's going to be the same as the minus x value. It's symmetric about the y-axis. Right? It also means that integral from minus a to a of f of x dx is just 2 times integral from 0 to a of f of x dx. Right? So this also cuts down on some of your work. This means, for example, that f of x times sine n pi x over L is odd, because an even function times an odd function is an odd function, which means if I integrate this from minus L to L, I will get 0, which means all the bn's will be 0. So what do we have? So this means if, so this is, if f is odd, this whole thing you can probably put in a box. So if f is odd, your formula actually gets smaller because all your a's will be 0. And so you only worry about the b's. And you don't even waste time with the a's because you're going to do all these integrations and you're going to end up with 0 at the answer. And these integrations in general are sort of tough, because immediately you can see, as long as your f is not constant, you're going to have to do by parts. Right? You're going to have a function times a sine. And if this guy doesn't die upon repeated differentiation, it's going to be a revolving integration by parts. Right? So you want to avoid integration if you can. Right? So knowing that a function is odd allows you to avoid some of the integration. So that's good. So this means if f is even, then we can write f of x will be a0 over 2 plus the sum equals 1 to infinity of a n cosine n pi x over L, where a0 is equal to this, a n is equal to this, 0 to L, x cosine n pi x over L dx, and your bn equals 0 for all of them. Fourier series for even functions are called cosine series. Find it out my intro. Another thing to note, given f of x on the interval like 0 to L or minus L to 0, we can choose to extend it as an odd or even I'm going to do some examples where we actually do this so you understand what I'm talking about. Yeah, so that's basically all the theory we need to know. So now I'm going to try to get through some examples. I have 5 here, but if I get through the first 3, I'll be happy. So the other 2 are just for variation. The principle will be the same. No pun intended. So yeah, so now we have a series of sines and cosines. And some of you are like, oh, Taylor series were bad enough with polynomials. Why do we even need these? It turns out for periodic functions, the Fourier series will actually converge a lot faster than the Taylor series will. And converging fast means it helps us to approximate things better using less terms of the series. Hence is what some of the uses of Fourier series are. It's used all over the place. Signal processing, audio compression, pretty much anything to do with waves, optics, right? You use a lot of Fourier series in optics because waves tend to be periodic, right? Light waves are periodic. You use it in heat transfer, which we're going to do in 10.5. I'm going to do an example of 10.5. Yeah.
Yeah, so if it's converging faster, doesn't that mean it's not as good as an approximation? Or why wouldn't that be the case?
No, approximating faster means you get really close to what the actual function is with less terms. That's actually better to approximate faster, right? It means, you know, approximating it to the 3rd term in a series that approaches faster is better. For another series, you might need 10 terms, right? And that's more computation, more information,
So
you need more space.
That doesn't converge for, like, let's say 50 terms, and we put down the first 5 terms, so we're putting down, like, what is that?
It's less of an approximation. It's farther from the actual answer. It turns out that the infinite series is the function, right? But if you only take a finite number of terms, you lose some information, so you can't get everything, right? So it's nice to have a series where you can use as little terms as possible and get closer to what the actual answer is, right? That we say that the series converges faster in that case. And that's good. So for example, in audio compression, how that works, right? So if you're like compressing an audio file to MP3 or something like that, what actually happens in the program is it converts the audio waves to Fourier series. The series are infinite, has a lot of information, but guess what? The human ear can only pick up a small range of sound waves, right? So they're like, a lot of the sound information is unnecessary. So what it does is it approximates the Fourier series. It just takes a finite number of terms of the Fourier series, enough terms for your human ear to not hear the difference. It cuts off the rest of the terms. And so now it re-encodes the new audio file with less information, right? But the information that's lost is information that you wouldn't be able to hear anyway. The series at the end are so small that you won't be able to pick up the decibels, right? So that's like some way that you can use Fourier series, right? So yeah, you're listening to your music on iPod, on your iPod, you're listening to Fourier series actually. So yeah, when math people say math is everywhere, we actually mean it. Example. Let's say f of x is, I give you the function, it's 2 on the interval 0, 1, it's 0 on the interval this, and I ask you to find this Fourier series. So here I gave you a function. They don't usually ask you to draw it. Like in the older finals, they did ask you to draw it, but I don't recall if in this round they did ask you to draw it. You don't need to draw it. Right, so this is your x-axis, your y-axis. What this function actually looks like is it goes from -1 to 1, so that automatically tells you your L is 1 in this case, right? So from 0 to 1, it is the function, the constant function 2. And from -1 to 0 is the constant function 0. Right? So really what the Fourier series of this thing would look like, it will repeat, this is -2, -3, -4, -5, It's going to repeat every 2 units, right? So it's going to repeat in here. You're going to have this. And over here, you're going to have this. Here, you're going to have this. And you're going to have this. So you sort of think of this going on forever, right? It's a periodic function, but they only have to tell you about how it looks around the origin, right? That's the thing that you want to repeat. Right? So you can assume that this function is repeating. This is sort of 10.3, but what's going to happen is you're going to approximate this with sines and cosines. So these guys are going to be a little wavy. They're going to jump up here and be a little wavy, and then come back down, be a little wavy, jump up, a little wavy. Right? Because it's sine and cosine, so it's approximating it by the constant function, right? So at first, the waves are way off target, right? But the more terms you use, they start getting like this. To the point where you approximate a straight line by this really jagged straight line, right? That's eventually what's going to happen when you get a lot of terms. But yeah, and if ever there's a jump continuity, the Fourier series will jump to the average point. Right, so it's going to plug in this point in between them and connect the dots there. Right, so that's what the Fourier series did. Not super important. This is sort of 10.3, but I thought I'd show you guys that. Let's actually compute the series. So we want f of x to be a0 over 2 plus the series from 1 to infinity of an cosine n pi x over L plus bn sine n pi x over L. Here, your L equals 1, right? So you're going to be able to plug that in. So this will mean your A0 is going to be 1 over 1 times the integral from -1 to 1 of f of x dx. But what is your f of x? From -1 to 0, it's nothing. So I can ignore that part of the integral, right? That's going to give me nothing. It's 0, from 0 to 1, it's actually the function 2. So this I can write as the integral. Yeah, I mean, technically, if you want to be technical, you'd actually do this plus from -1 to 0, then from 0 to 1, you would do the function 2. But of course, if something is 0, just ignore that part. It's not a part of it. We don't have to worry about it. So really, your A0 is going to be given for the integral from 0 to 1 of 2. So this is going to be 2x between 0 and 1, which is just 2. Right? So this means that your A0 over 2 component is just 1. Right? That's going to be, the first term here is going to be 1. Let's find the AN terms. For AN, what that's going to be is going to be 1 over L, integral from -L to L, f of x cosine n pi x over L x. But this is just, again, we can ignore the part from -1 to 0, just start from 0 to 1 of the function 2 cosine n pi x over 1 dx. So now, what's the integral of cosine n pi x?
Sine n pi,
Sine n pi x.
times n.
No. Antiderivative.
1 over n.
1 over n pi. N pi is a constant. So this is 2 over n pi times sine n pi x between 0 and 1. What's going to happen here?
0 cancels.
Plug in 1 for x, so this is 2 over n pi times sine of n pi minus Plug in sine of 0, you get 0. But what's sine of n pi?
0.
It's actually 0. So there's going to be no general an term. But you see, not all the a's were 0. Your a0, in fact, was not 0. And what the reason for that is it's not exactly an odd function. Turns out it would be an odd function if we had just shifted down by a half, right? And so that's why most of your a's are 0, but not all of them. So technically it's not an odd function, but it's very close to 1. It's just an upward shift of an odd function. That's what this plus 1 is about. The constant term is just the vertical shift, right? We remember that from pre-calc, because we're all experts at the previous math classes. Okay, so now we know that all an's except the first one is 0. And what about the bn's? Well, this is 1 over L times minus L to L of f of x sine n pi x over L dx. So this is 1 over 1 times from 0 to 1, because from minus 1 to 0, it's 0. 2 sine n pi x over 1 dx. Integral of sine n pi x. Integral of sine n pi x.
1 over negative 1 over
Negative 1 over n pi cosine n pi x. Between 0 and 1. So now we have plug in 1, we get cosine n pi minus plug in 0. Cosine of 0 is 1, so this just becomes plus 2 over n pi. Do I want to show you that? We can write this in a nicer form, but let's not do it for now. I'll probably do it afterwards. So yeah, that's your bn. This means this f of x that you just given me, I can write it as 1 plus the sum from 1 to infinity of bn plus 2 over n pi times sine n pi x. And so for that function, the function that takes on the value 2 from 0 to 1 and 0 from 0 to negative 1, that's the Fourier series for this guy. So that's going to be the guy that looks like right? And the more terms you get, the more these guys will get closer to the straight line. So that's your guy. Note. You could have written this in another form. So if we see something like minus 2 over n pi cosine n pi plus 2 over n pi, right? There are actually a couple things that this could be equal to. For example, how does cosine of n pi behave?
even function.
Right, it changes whether n is even or odd, right? So if n is even, what happens? What is cosine n pi when n is even? It's positive 1, right? So it would be minus 2 over n pi times positive 1 plus 2 over n pi equals 0 if n is even. And if n is odd, what does it give you? It gives you a negative 1, right? So it will be minus 2 over n pi times negative 1 plus 2 over n pi, which is equal to just 4 over n pi if n is odd. So you can even get rid of more information. Don't count all n's, only count the odd ones, because all the even ones are going to be 0. So an alternative way to write the solution to this guy alternatively, I can write f of x is equal 1 plus the summation for all odd integers of 4 over n pi sine n pi x, which looks nicer, it brings less information. Or if you wanted to write it as a whole series, 1 plus, you can say something like k from 1 to infinity of 4 over 2k minus 1 pi sine of 2k minus 1 pi x. Right? So that would only give you odd numbers. Right? 2k plus or minus 1 is always an odd number. So it's just a nicer way to write it. Back when I did differential equations, they expected you to go to here. It seems these days this is okay for these kids. I believe even in Boyce and Dupree, if I'm not mistaken, one of the old versions would have this as the answer, but in the current edition, this is the answer. Like they say you can skip this part. Maybe. I feel like there's a textbook that I read that when they changed editions, they just, forget about this. Don't worry about the truth.
Is there a way now you can convert that to a continuous function?
What?
Meaning now we have a series, which is
This is a continuous function.
That is a continuous function.
It's a sum of sines and cosines. It's a sum of sines. Sines are a continuous function. The sum of continuous functions are continuous. Right. So this is just 1 plus some amount of sines, right? It's sine of pi x plus sine of 2 pi x plus sine of 3 pi x plus sine of 4 pi x with these coefficients. So yeah. So this guy, it looks like 1 plus 4 over pi sine of pi x plus 4 over 2, 4 over 3 pi sine of 3 pi x plus 4 over 5 pi sine of 5 pi x plus, it continues like that. So it's sort of continuous, right? It'll look like this. So your function was discontinuous, it had jumps, but when we switch it here, it sort of smooths things out. So let's do another example. So I mean, either one of these answers is fine. I'll go easy on you guys. You might get brownie points for writing this way. Might let something else slide. Oh, you dropped the negative sign, but you did this. All right. Otherwise, you dropped a negative sign and you did that. Minus 10. I'm kidding. Okay, I'm kidding. All right. So here's one where we're going to extend it, right? So given, I'm going to make it very similar to this function, but I want it to be odd. So given f of x equals 2 on 0 to 1, you could be asked to say something like, find the sine series. Or they could say something like, extend it as an odd function and find its Fourier series. Two different ways to say exactly the same thing, right? Because if it's an odd function, then its Fourier series will actually be a sine series, right? But basically that means, what does it mean if it's a sine series? What does that help me to avoid?
The cosine.
All the a's are 0. So all the cosine, so the cosine part of the series, ignore it. And even this part, ignore it. It's not going to be a factor. So basically what's going to happen is, so here's my function. From 0 to 1, it is the function 2. And that's all the information I'm given. So when they say extend it as an odd function, it means how would I extend it? How would it look like on this interval? What would the function be on this interval? Minus 1 to 0. It can't be the same thing. It can't be the same. Because in that case, f of x will be the same as f of minus x.
0?
It wouldn't be 0. What makes something odd? F of minus x should be what?
Negative 1.
The negative of f of x. So if f of x is 2 on this side, what should it be on this side?
Negative 2.
Minus 2. Right? So that's the pattern you're going to repeat. Right? So this guy just goes like, and it repeats that way. So that's what the odd version of the previous question would look like. It wouldn't be at 0. It would actually need to be down here to be odd. So this is sort of the thing I want to find the Fourier series for. So basically, since they say find the sine series, or it's an odd function, find the series, since f is odd, we know that our a n is equals 0 for all n. So ignore it. I only need to find the bn. Bn would be equal to 2 over L times the integral from 0 to L of f of x sine n pi x over L. This will be, our L in this case is what? It's also 1. So this is 2 over 1 times the integral from 0 to 1. F of x is just the function 2 sine n pi x. All right, so remember L is just half the period. We saw that the function was periodic on this interval. Right? So the period is length 2, right? Which means, so here the period equals 2. But remember, we set the period to be 2L periodic, right? Which means that your L has to be 1. You can, if you're ever never sure, just look at around the center, what's the period, and then you take half of it. That's going to be your L. Okay, so this guy will be equal to, we did this before, this is minus 2 over n pi sine cosine n pi x times the 2 from here. This is between 0 and 1. So it's going to be minus 4 over n pi sine n pi plus, plug in 0, you just get 4 over n pi, which we know this will be equal to 0 if n is even. It will be equal to 8 over n pi if n is odd. This means f of x is equal to the series over all odd integers 8 over n pi sine n pi x. Or, if you want to be lazy, you can just say this is f of x equals, this long n goes from 1 to infinity of, and you put this whole thing, minus 4 over n pi cosine n pi plus 4 over n pi sine n pi x. So if you're given that your function is odd, it saves you a lot of work, because you can just forget about the a's and only worry about the b's, right? So that's nice. I'll also give you an example where you can forget about the b's and only do the a's. That's when we're actually extended as an even function. Example. Given f of x equals, I'm going to keep it similar so we don't have to use too much Gaussian. 2 from 0 x 1 0 on 1 x 2 extend this as an even function and find its Fourier series. Or they could say, they could just give you this and say, find the cosine series. And they expect you to know, okay, I'm going to think of it as even, and only worry about the an's. So, let's do this. Since f is even, bn equals 0 for all n. Now we only have to worry about the a's. So let's start with a0. This is the integral of 2 over L from minus L to L of f of x. So what is L in this case?
0.
Okay.
From 0 to 1.
What does this function look like?
3 over 2.
It's 2 from 0 to 1, and it's 0 from 1 to 2. So it looks like this, and then it looks like that. This is half the period, right? This thing I'm going to want to repeat over here in such a way that it's even, which means it's going to connect here, and then continue like that, right? And so this thing is going to keep branching off.
Equal to
Hmm?
L equal to?
L equals 2, right? Because a full period would be 4. Notice that they only gave you the part starting at 0 going all the way up to 2. Right? So the end point from 0 is going to be your L. L is 2 in this case. So this is 2 over 2 times integral from minus 2 to 2. Well, from this would be 0. From 0 to 2 of f of x. But in this case, on 1 to 2, it's nothing, right? It's 0. So I can only do all my integrals from 0 to 1, and it'll work. So I'm just going to do an integral from 0 to 1 of f, which is just 2 dx. This is 2x from 0 to 1, which is 2. Which means a0 over 2 is 1. That's going to be the first term. N will be 2 over L integral from minus L to L f of x cosine pi x over L x. This is 2 over 2 integral from 0 to 1 of 2 cosine n pi x over 2 dx. Those 2's cancel. So this will be 2 over, what's the integral of cosine of n pi x over 2?
Negative n pi over 2.
No. You're taking the derivative.
Oh.
I'm just thinking. I was like, wait,
Okay, so
wrong direction.
2 over n pi.
2 over n pi, right? The constant is just n pi over 2. So you flip the constant and multiply. So that's going to be 4 over n pi. It stays positive because we're doing integral. Sine of n pi x over 2 between 0 and 1, which means this is 4 over n pi sine of n pi over 2 minus 0. Okay, and so this means f of x equals 1 plus the series n goes from 1 to infinity of this guy, 4 over n pi sine n pi over 2 times cosine n pi x over 2. We could find a formula for this, but it'll be 4 terms, so I'm not even going to bother. Because when your n is odd or even, there are actually a couple things it could be. It can be, well, if your n is even, you get 0, but if your n is like 1, you'll get positive 1. If your n is like 3, you'll get minus 1. You know, there are like 3 cases I don't want to bother with. So I write this as 8.
I have a question. So, at this one part, when you equate is a0 over 2 equal 1. So, where you get
Yeah, because remember in the general formula, your f of x is a0 over 2 plus the series of blah, blah, blah. So I always want to know a0 over 2.
Okay. But I'm saying when you equate it equal 1, why do you do equal 1?
Because a0 was 2, so just 2 over 2 is, I'm just writing that down. I always like to write this down because sometimes students forget, they just write the 2 here. Right, so I always remind myself, I write it down right away. Once I find a0 over 2 is this. So I have that and I circle it. So that if I'm in a final, I don't forget that I'm using the 1 and not the 2. Find the Fourier series. Of f of x equals sine 2 pi x minus sine 5 pi x. So that's an odd function because it only has signs in it. So I know we have no choice but to extend it as an odd function. It'd be really weird to extend it as an even function. So what is going to happen here? So we could say, you know what, ignore ANs. Our BNs would be equal to 2 over L, which is 1, integral from 0 to 1, of sine of 2 pi x minus sine of 5 pi x times sine of n pi x over 1 dx. So now, how do you integrate this guy? Going to be a crazy by parts. You can get away from by parts by using something that called the product to sum formulas, which we all remember from pre-calc. Okay, no one remembers that. Right, so if you do this, you're not thinking. Right? It's a trick question. Because this is what? It's a sum of sines. What is a Fourier series? A sum of sines and cosines. Functions that are sines and cosines already are their own Fourier series. The Fourier series is, this is the Fourier series.
You're realizing this not on the final.
Right. So I'm just giving you a heads up. What would have happened is you would have gone through some complicated integration. You realize that something is going to happen that's going to cause you to divide by 0 in pretty much every term except the second and the fifth term. And so the second and the fifth term will be the only guys that end up. But it's after a really long thing. You know. I actually did it when I first learned this. I did it, and I'm like, holy crap! There has to be an easier way. And then I was like, so yeah, so that's that. That was just a kid example. You'll need it in 10.5. I think there are some problems where they actually do stuff with functions like this. Okay. Let's do a slightly harder example. This is actually from fall 2011. And the question was to find the sine series of f of x equals x times 1 minus x on the interval 0, 1. I don't think it asks you to draw it, but you do that for fun. What does this look like? It's a quadratic. What does it look like? What are the intercepts?
It's a parabola.
Yeah, it's a parabola. So
It's a negative parabola, so it's upside down.
yeah, so intercepts are 0 and 1, and the parabola goes like this, right? Now you're going to want to extend this as a sine series, which means the rest of it is going to be like 2 minus 1 and 1. And then this pattern is going to repeat. Now it would sort of look like a sine function, but technically it's not a sine function, it's a polynomial, right? It's going to behave very differently. But it sort of stands to reason that a sine series would be the optimal series to use if you wanted to do something like that. So, since f is odd, a n's would be what? 0 for all n. And the bn would be 2 over L integral from minus L to L f of x sine n pi x over L dx. What's L in this case? It's 1. So this is 2 over 1. I forget. For this one, I'm doubling it and starting at 0. So this is 0 to 1 of f of x, x times x times 1 minus x, sine n pi x over 1. How do you integrate that?
Substitution.
Substitution? No. Substitution of parts. So polynomial times the trig function. So it's going to be a by parts. So we have 2, 0 to 1. I'd probably just write this as a single polynomial instead of a product of 2. So write this as x minus x squared times sine n pi x dx. Now how do we do with that pattern? How do you do that?
Next one will be the u.
I can differentiate this and it will go to 0 eventually. I'd use the tabular method. Because you have to use integration by parts twice. I just start differentiating. Differentiate derivative is 1 minus 2x. Derivative of that is minus 2. Derivative of that is 0. plus sign's going to be here, minus sign's going to be here, plus sign's going to be here. Integrate this. Integral of sine n pi is?
Negative 1 over n pi cosine
Minus 1 over n pi cosine n pi x. Integral of that is?
Over n
negative
squared, pi squared.
Negative 1 over n squared pi squared sine n pi x. Integral of that is?
1 over n cubed, pi cubed.
1 over n cubed pi cubed cosine n pi x. Alright, so the first term is going to be given by this guy. So we have 2 times integral of 0 to 1 of x minus x squared sine n pi x dx. That's going to be equal to 2 times, the first term is going to be this guy times a positive, so he ends up with negative x minus x squared over n pi cosine n pi x. The next guy is going to be this with a negative, so that's going to be positive 1 minus 2x over n squared pi squared sine n pi x. Next guy is going to be this one times a positive sign, so this would be negative 2 over n cubed pi cubed cosine n pi x. This is between 0 and 1. Now if I plug in 1 into the sine, I get sine of n pi, and 0 into sine, I would get 0 in either case, so this term dies. Right? I know that's going to be 0. If I plug in 1 here, if I have x minus x squared, and I plug in 1, that will also be 0. If I plug in 0 for this, x is 0 and 0, that would also be 0. So this term is also 0, so we can ignore that. We're only plugging into this term, ultimately. So this ends up being 2, plug in 1 here, 2 over n, minus 2 over n cubed pi cubed cosine n pi, plus 2 over n cubed pi cubed. So this means our f of x, this particular f of x, we can write as, well, this I can simplify this. So when n is even, this gives me a plus 1, which means this will be 0. So 0 if n even. And if n is odd, I get 4 times 2. It's 8 over n cubed pi cubed if n is odd. So my Fourier series would be the sum odd, overall odd integers, so it only counts 1, 3, 5, 7, 9 of 8 over n cubed pi cubed sine n pi x over L, which is 1. And if you did that integration by parts, you'd still be working on this it at this point. It's probably on the second step. But yeah, that's sort of it. Are there any questions? Yeah. So ultimately, it's one of these sort of plug and chug problems. It can sort of be annoying, especially if your f of x is annoying and you have to do by parts or something silly like that. But it comes down to, you know the formula, you have to know what in general what a Fourier series looks like, and then know the integrals that give you the coefficients. And then you have to know if it's odd or even, you can ignore some of them so that it saves you time. Yeah.
Yeah, so you were talking about how a Fourier series helps you because you can use it to approximate a function.
Yeah, series in general help
Right.
you in this way.
But so when we extended it as an odd function, where we had to negate it, so how does that account us for, like, it doesn't represent the real function?
What do you?
I mean,
Oh, like here? Yeah, well, ultimately, all we were given was this information, right? So think of it this way. Let's say, you have your friend who says, yo man, I came up with a sick beat, yo. And he just plays you like a 5-second clip of it. Right? Now you want to make a whole song, right? So 5 seconds is enough. So what are you going to do? You're going to want to repeat that beat, right? Now it depends on if you want to flip the beat at some point. You might want to do it an odd way, right? Or if you just want to maintain the same beat throughout the whole song, you'd extend it in an even way. So you sort of choose what you want at any given time. So sometimes you're given a little information, but you want to repeat that same information for some reason. Right? And that's how you say, okay, turn it into a Fourier series to repeat this guy, then approximate it with a finite number of terms to save on information or compress the file, and that's how you proceed. So yeah, it all boils down to what you want to accomplish with it. I mean, in general, when you get to the point where you'll actually apply this, you'll know what you'll need to do. Hopefully, if you remember your calculus. But yeah, that's it for today's class. So yeah, it's crunch time. You're pretty much going to have very little study time for the 4th test and the final, right? So our final is the Monday. Our final is a week from today, right?
Yes. No,
Today's Wednesday.
exam 4 is
Exam 4 is a week from today.
Okay.
The final is the Monday right
after.
after that.
Exam
So,
is going to be Fourier Series and Laplace.
yeah, so for the fourth exam, it's very short. It's 2 problems. I'm going to ask you a Laplace question and a Fourier series question. So it's going to be like a half-hour exam or something.
So that's a week from today.
Yeah. So so we're going to have an exam and then take a nap or something because it's like 8 a.m. But yeah, I'm thinking of maybe having a mock final that weekend or something. I don't know how many people will be able to show up for that. So we'll talk about the details a little later. But for now, this is Fourier series.
About the size of the cover. What do you do with the